We are currently transitioning the world's transportation and power infrastructure away from internal combustion and toward battery electric vehicles and renewable grids. In 2024, global greenhouse gas emissions reached an all-time high of 53.2 gigatons. To alter that atmospheric trajectory, the international community has focused on a single, indispensable element: lithium. Lithium is the lightest solid metal on the periodic table. Its unique atomic structure allows it to shed electrons with ease, making it a highly reactive and efficient medium for electrochemical energy storage. This high energy density makes lithium essential for stabilizing electrical grids. Large utility-scale storage systems capture intermittent solar and wind power, smoothing out supply gaps to ensure the lights stay on when the sun goes down. Deploying clean electrons via these batteries represents the fastest lever available to policymakers seeking to permanently slash emissions. This demand curve is steep. To meet announced climate pledges, the International Energy Agency projects that global lithium demand must rise from roughly 101 kilotons in 2021 to 531 kilotons by 2030. Despite the environmental cost of that growth, the operational phase of an electric vehicle eventually overcomes its manufacturing footprint. After roughly 2 years of driving, a battery electric vehicle crosses its carbon payback threshold, offsetting its initial manufacturing debt. However, achieving that life cycle efficiency requires a massive initial investment of materials. A standard electric vehicle requires 6 times the mineral inputs of a conventional automobile. This is the clean energy paradox. Fundamentally altering the composition of our atmosphere requires an aggressive, massive excavation of the Earth's crust. In South America, that excavation is centered on the Lithium Triangle, a high-altitude desert holding up to 65% of the world's known reserves within subterranean aquifers. To extract it, lithium-rich brine is pumped from deep underground into massive surface ponds. Over 12 to 24 months, the desert sun evaporates the water, concentrating the lithium salts for processing. This process is incredibly water-intensive. Producing a single ton of lithium using traditional evaporation requires up to 2 million liters of water in one of the most arid environments on Earth. This constant pumping alters the basin's hydrology and devastates unique biodiversity, like these Andean flamingos, relying on the fragile high-altitude lagoons that are now disappearing. Indigenous communities often see their sacred lands disrupted without their fundamental right to consent, leading to widespread protests, occasionally met with severe state repression. Leveraging free solar energy makes this the most cost-effective extraction method, but it forces a direct sacrifice of local water resources and the rights of frontline communities. The alternative is hard rock extraction, primarily the heavy industrial open-pit mining of spodumene ore, a process currently led by Australia. While hard rock mining saves water, it is significantly more carbon-intensive. Because the raw ore is typically refined using coal-heavy electricity grids, it produces 3 times more carbon emissions than brine extraction. Beyond industrial mines, the global scramble for minerals has fueled an aggressive investment surge in Zimbabwe, home to Africa's largest lithium reserves. Thousands of informal miners, including children, work in this unregulated artisanal sector. They extract ore using basic hand tools in dangerous environments for their survival. Trading brine for hard rock simply shifts the burden from a regional water crisis to increased atmospheric pollution and human exploitation. Extraction is only the first stage of the supply chain. Strategic leverage is actually held by the midstream chemical processing and refining sector. Through decades of targeted subsidies, China secured a near monopoly on this stage and is projected to control 81% of global spodumene refining capacity by 2027. Western nations are now attempting to break this dependency. The U.S. Inflation Reduction Act provides billions to forcefully onshore battery production and mineral processing. For now, the global transition to a decarbonized economy remains tethered to a supply chain controlled by a single geopolitical rival. The industry is racing to develop direct lithium extraction, or DLE, to reconcile these environmental costs. DLE plants use specialized chemical sorbents to selectively capture lithium ions directly from the brine as it is pumped through the system. Crucially, the lithium-depleted water is then re-injected back underground, preserving aquifer pressure and drastically reducing the need for sprawling surface ponds. Alternatives like sodium-ion batteries are also emerging for stationary grid storage, which could eventually reduce the aggregate pressure on the lithium supply. While DLE requires high upfront capital, it is the most viable path toward preventing the total exhaustion of high-altitude desert ecosystems. The ultimate goal is the creation of a circular economy through urban mining, the advanced recycling of end-of-life batteries. Recycling bypasses the most carbon-heavy phases of mining and smelting, slashing greenhouse gas emissions by up to 81% compared to producing virgin metals. However, because the mass adoption of electric vehicles only recently accelerated, the volume of batteries available for recycling won't hit a meaningful scale until after 2030. We are successfully removing emissions from the tailpipe, but we are currently transferring that environmental weight directly to the mine. The shift toward electrification will only reach its full potential once we move past this destructive extraction phase and establish an infinite recycling loop.